I was wondering what role the media has in these misconceptions. They tend to be quite sensationalist, and what can we do about that?
Yeah, that's a really great question. And it's sort of, it is related to this issue of misinformation, disinformation, the spread of those kinds of things online. I'm not really sure exactly what we can do about it. I've got some colleagues that are trying to work on that issue at the moment. Yeah, I think there is evidence that if you're exposed to certain kinds of media, you do tend to have certain perceptions. So one strategy would be for just all of us to be considering what kind of media you're being exposed to, and not and also considering, you know, how your search behaviors lead to what you're seeing online. But yeah, I think I would suggest having a look at the paper that I mentioned, because we have a section talking about that in there.
Great presentation. Thank you. That was really interesting. I had a question about if this research has made you more hopeful or more pessimistic in terms of kind of identifying why we might be misperceiving each other, but also you know, maybe now that we've identified it, that could be helpful. I don't know. How do you feel about these outcomes?
Yeah, that's a great question. I think that it's made me more optimistic. I think that, you know, part of the problem with a misperception is if no one's aware that that's happening. So if we can draw attention to this, and I think researchers are increasingly talking about this and providing evidence showing this. So I think we're reaching a point now where we can start to talk more openly about it, and then maybe correct some of the things that are happening. So yeah, thank you.
Yeah, interesting talk. Do you see any funded group out there really advocating this to the Joe public? You know, we've got all this information you can get from the internet, anything you want, as you say, but there doesn't seem to be, you know, just a normal voice out there pushing the subject.
Yeah, I mean, I guess it might depend on the country that you're looking at. So I think yeah, I mentioned the Yale Centre for Climate Change Communication. I think they do a lot of trying to talk about what is the actual state of things, but then they are focused on the US context, so that's not that useful for.
I'm just talking about the average person thinking, actually, I can do something worthwhile without having to spend a lot of money. You know, there's ways, but nobody's sort of talking to those people. I wouldn't have thought, you know.
Yeah, I think it's an area for development for sure. I think we could be talking. I think universities often I think have an obligation to be engaging more with the average person and bringing these kinds of findings, and then you know, helping people figure out what they can do. So yeah, I would say that maybe people in the universities could start thinking how to bring this more to people.
If there are no further questions, well, thanks, Maddie, again.
Thank you.
Okay, so the next speaker is Anthony Mirfin. Where's Anthony? Oh, over there. Yep. And he's going to be talking about a data-driven model of energy, building energy consumption.
Thanks, Michael. So yeah, my name's Anthony. I'm a PhD student in the Department of Physics here, and Michael's actually my supervisor. So yeah, we're going to be talking about how we can incorporate solar gain into these building energy models. So I'll just start by defining what these are. So we're trying to predict the energy consumption of a building. So this could be an office building, could be a house. We're going to do this at a fine time scale. So this could be like hourly or half hourly points. Some of the applications of these, so we can optimize the use of smart buildings. fault detection. So if we predict the energy use of a building and then we observe that it's completely different to that, there might be something wrong with it. And we can also measure the savings of efficiency improvements. So that's this plot here on the right. So the idea being you take your business as usual unimproved building, you forecast its energy use, and then you go and observe the actual improved building, and you take the difference to be your savings. And with the fine time step, you can see what time of day those savings occur. So that's showing the value of those savings. So I'll explain what I mean by a data-driven model. So the only inputs to the model are historic energy consumption data and weather data. So we don't require any building-specific information. So things like building materials, dimensions, because these are often time-consuming and difficult to gather. Machine learning models are one example, or statistical models are another example. And we're going to be looking at the stats models in this treatment. So these models typically just use temperature as an explanatory variable, but they don't include solar. But we know that solar gain impacts the energy demand of a building. So the solar gain is the actual increase in thermal energy demand of the building, and that just depends on how much sunlight comes in through the windows. So obviously that's going to change how much you need to heat or cool your building. So we're going to add this into the model to try and improve the accuracy. But it's not straightforward, and that complexity is one of the main reasons that other models haven't really gone into this detail. So in terms of how we're going to add solar into the model, we need to look at the physics description. So if a building's heating to some internal temperature, say 20 degrees, there is heat loss that's proportional to the temperature difference inside and outside. So we have to supply heat to make up that heat loss. But we also have solar coming in through the windows, so that reduces how much heat you have to supply from your heater. When it's cooling though, solar is acting in the opposite way. So if you have more sunlight coming in while you're trying to cool your house or a building, then you actually need to supply more energy to cool it down. So from this, we see that solar acts in opposite ways on the energy demand of a building, depending on whether it's heating or cooling. So some of the insights from that physics description, we need to use the actual solar gain. So that's how much sunlight is coming in through the windows. So this isn't available from weather data, but we have a model for this. So the first term is the diffuse or scattered solar. The second term is the direct or beam solar that comes in through each window. So that subscript W is referring to each window, and then we're going to add up the solar for each of those windows. In terms of each of the terms in this model, some of them are just parameters. They're going to be fit by the stats model. So that's sort of analogous to the slope of your line through some data points. And then the interesting term is that IW on the right. So that is not available from weather data, but we can calculate it if we know what way the window is facing, basically. The other insight that we saw was that solar has a different effect depending on whether it's heating or cooling. So we're going to have to treat that differently in the model. In order to do that, we need some knowledge of when the building is heating and when it's cooling. So we're going to look more at this irradiance on each window and how we can deal with that. So from the weather data, we have what's called global horizontal irradiance. So that's the solar received by a flat plane. But what we want to do is calculate that irradiance on a vertical plane, so like a window. But we need to know that orientation of the window. So what way is it pointing? Is it pointing north, 15 degrees from north? But we don't know that for a building. And we assume these are all going to be data-driven models. So we're not going to supply any of this information. So how can we deal with those unknowns? We're going to simplify the case. Let's just assume that the building is some rectangle. So each of the facades with the windows are going to be 90 degrees from each other. So it could look something like that L-shaped building or anything like that. The reason for doing this is now we only have one unknown orientation parameter, which describes all of the windows. So in order to deal with this unknown, we're just going to test the range of orientations, and we're going to pick the orientation that gives the best final model fit. So basically the model is working out the window orientations through optimizing the model fit. The other insight that we saw was to treat it differently for heating and cooling. Again, we assume we don't know this information of when the building's heating and when it's cooling. But we can work it out if we cluster based on solar gain and temperature. And so this clustering uses the modeled solar gain. So again, that's not available in weather data, but we can estimate it using that equation we saw before. Here we just show some results. So the left-hand column is the industry standard model, which doesn't account for solar. The right-hand column is our model. The table is just showing a measure of model error. So the lower, the better. The data that we used for this was simulated data. So we basically had a test case building that we tested in different climates. And we did that for a lightweight building and a heavyweight building. So that top table is for the lightweight case, and the other one is the heavyweight case. And basically, we just see that our model does significantly better in all cases. Some more results that we can look at. So on the left is a scatter plot of actual demand versus model predictions. So say, for example, the actual demand was 4 kilowatts, then we hope our prediction is going to be close to that. So a better model is going to be closer to that 45-degree line. And that's the industry standard model in blue, our model in red. The other interesting plot we can look at is the time series of model predictions against the actual demand. And I've also plotted on this graph the estimated solar gain. So the idea with the time series is you can see when the model was doing better or worse, and we can sort of link that to the solar gain. So we see that the industry model, which doesn't account for solar, consistently under or over predicts in line with that solar gain, whereas our model follows the actual demand a lot closer. Some additional results from our model fitting process. So we had to distinguish the heating and cooling times. So that's that plot on the left. And we had an accuracy of about 98, 99% with that. And then the plot on the right is showing the model fit based on assumed orientation. So the bottom line is for the heavyweight case, the top line is for the lightweight case. And so that is for the assumed orientation that we put into the model. In the actual model fitting process, we take the best of these. So we take the lowest point, and that's how we optimize for orientation. But this plot is just showing that orientation is an important consideration, as the worst model fit on there is about 30% greater in terms of model error than the best. So in terms of future work, since we've applied this to simulated data sets, we're looking at going on to real data next. So they'll be used for testing model robustness, especially. And that method of identifying the heating and cooling times will likely need to be revised due to more noisy data. So we think we'll have to make that a bit more sophisticated. So using information of neighboring times are more likely to be the same. So if it's heating at one point, it's more likely to be heating at the next time step than it would be cooling. So using that temporal information. Thank you.
Thanks, Anthony. So how often do you go to a conference where you hear a psychology presentation and then a physics one straight after? Any questions, please?
Thanks, Anthony. It's a great work indeed. Just a very brief question. When you're looking at the solar gain profiles or the computations, do you take into account double glazing, triple glazing versus single glazing, as there will be some reduction with, especially with triple glazing?
Yeah. So in terms of transmissivity, they will have different amounts of solar that those windows actually let in. The idea with this model is that will all be captured by a parameter that's fit by the model. So we take the irradiance to be the irradiance that falls on the outside of the window, and that's just per meters squared of window. And then we've got a parameter that multiplies that will depend on window area and also how much solar irradiance actually comes through the window. So that's all captured by parameters that are fit by the model.
Thanks.
Any other questions? Anything online? Okay, so just so,
who do you think will be the main users of this information? Is it actually air conditioning people, or is it building design from the onset, or retrofitting, or a combination of all of the above?
Yeah. So there are lots of use cases for sure. So be of interest to lots of different players in the energy sector. But I think the most promising application is that retrofitting and assessing the actual savings of your improvements, and then seeing, what time of year and what time of day are those savings being realized.
Yeah, our building codes moved away from using solar gain and thermal mass as being things that we look at and can consider in the H1 calculations and so on, which seems a real shame. But, is this research going to be able to, get us numbers that we can bring these things back a bit more?
Right. Yeah, I think it definitely has that potential for application in that. So one of the advantages of these statistical models compared to machine learning is that we can interpret them more easily. So we'll be able to see what the actual contribution from solar is to that energy demand. So we should be able to separate that out from the temperature component fairly easily.
okay, I'll think we'll bring it to a close, and just Anthony wants data, if anyone has real data for real buildings. So let's thank Anthony again. So our next speaker is Kieran DeMonte, also from the University of Otago, and he's going to talk about catalysts for hydrogen production, I presume?
CO2 reduction.
CO2 reduction. Okay.
Good afternoon, everyone. My name is Kieran DeMonte. I'm a second-year PhD student here at the University of Otago in Professor Sally Brooker's group. So we've had psychology, physics, I'm going to throw in some chemistry. So I make designer catalysts for CO2 electroreduction. So we'll get into it. So as we all know, global warming is a massive problem that faces us as a species. And this graph, which we will probably seen before, just shows predicted warming with different levels of greenhouse gas emissions. And ideally, we want to be down this optimistic scenario, the 1.5 degrees compatible, well below the 2 degrees. So CO2 is one of these greenhouse gases, and the aim is to cut fossil fuel use, which produces CO2, which we release into the atmosphere, and reach these kind of standards where we're actually capturing and utilizing the CO2 that we release. So we can create these closed carbon loops by taking the CO2 from our waste streams and converting them into renewable carbon fuels or value-added carbon products, which then, during combustion creates this closed loop and reduces the amount we're actually emitting into the atmosphere. So we can do this through electroreduction. And this table here just shows a few of the products that we can get by reducing carbon dioxide in the presence of protons. So we can get formic acid, carbon monoxide, methane, methanol, etc., etc. And the potential shown here don't seem very high. However, this is the potentials to start forming these products. And if you want to start forming them on an industrial scale at a good enough rate, you're going to need to provide large overpotentials, high driving forces to actually get a decent amount of them. And that also gives you the problem of selectivity. Because these are all so close together, if you just did this process, you would get a mixture, which is difficult to separate and is very energy intensive to separate. So we can have catalysts that provide selectivity towards certain products. So a lot of catalysts that have been used industrially are in aqueous or homogeneous solutions. However, molecular catalysts tend to not perform very well or for very long in these conditions. They tend to just break apart. So one way that we can improve the efficiency and stability of these is by mobilizing them on a surface and performing electroreduction that way in a heterogeneous system. So looking back in the literature, this has only been happening for sort of the past 10 years, with 2013 being the first example of a molecular catalyst for CO2 electroreduction being deposited on a surface. Now, the main thing to note about these examples is these sort of carbon ring systems, sort of over here, which are useful for deposition, which we'll see in a bit. The example highlighted on the bottom left there is a collaboration between our group and Professor Aaron Marshall's group up in the engineering labs in Canterbury, which this project is also a collaboration on as well. So my target catalysts were these ones, which were made back in 2004 in our group. However, they were characterized, but they weren't tested in any way. So they're made from pretty readily available, cheap starting materials. The synthesis, very, very quick, can be done in a day, and also uses first row transition metals, so quite readily available. These complexes also have these sort of conjugated carbon ring systems, and they're more stable because of this sort of macrocyclic effect. They can kind of clip onto the metals quite nicely. These complexes, however, are pretty insoluble in most solvents. However, this makes them an ideal candidate for depositing onto a surface because they won't be washed off or dissolved by water. And as well, there's two metals in the system, whereas before in all the examples, they were only have one metal. So the idea is that these metals could work in cooperation, potentially forming different products. So there's a few ways that we can do surface mobilization. We can do covalent surface attachment, which is actually make a bond between the catalyst and our surface through chemical reactions. And this could provide a good monolayer coverage. However, this can be quite difficult and our catalysts don't have that functionality. So a much easier method is to do non-covalent surface mobilization, which is using these carbon ring systems, which basically when you deposit it on another carbon surface, they act like Velcro and kind of stick and stay put. And then you can also do pyrolysis, which is heating them up and cooking them onto the surface potentially. And we can do this by just drop casting, letting it dry, or by surface spraying, which is what we did in this case. So we use this setup. We have our suspension of catalyst, carbon black, and other things, and we spray it across our carbon felt electrode. And to get a nice even coating, we heat it to 120 degrees, so it evaporates the solvent as it goes, so you don't get any agglomeration onto that surface. You get a nice even layer. And then we take our treated electrode and we put it into our flow cell, which has a potassium bicarb as our electrolyte flowing around. So what happens is our saturated electrolyte flows through our cell. So the electrolyte's in here, flows through our cell, and ideally the carbon dioxide is converted into carbon monoxide and other carbon products. So we do chronoamperometry. So we hold the cell at a certain voltage, so minus 1.1, minus 1.2, through to minus 1.7. And then we measure the gaseous products that are released through gas chromatography, the GC seen in the back there. And then we keep our solutions at the end for liquid product analysis. So the results, when we talk about tons, is turnover number is basically just the amount of product you get per amount of catalysts you've got in there. So all of our catalysts have this ongoing activity after our 50-minute run at all potentials, which is great because it highlights the higher stability of our catalysts on the surfaces. So our two major products are hydrogen and carbon monoxide. Hydrogen obviously is not a carbon product and is more of a side product that we don't necessarily want. However, the right mixture of hydrogen and carbon monoxide is syngas, which can be used for the synthesis of other carbon fuels. So that's good. But in this case, if you note the scales, we have sort of 4,000 compared to 250. So that's not a great ratio. So it is obviously the dominating product. However, the copper complexes do show good activity for the hydrogen production, definitely compared to the nickel, which shows sort of similar activity to the blank control runs that we did. And this complex up at the top here is our highest performer by far. And we can see that, you know, at this sort of potential, it does outstrip the others by quite a lot. And the nickel is sort of sitting down towards the blank. And our carbon monoxide, our copper complexes are actually pretty close in their in terms of their activities. And in this case, the nickel complexes actually perform lower than the blanks, which you can see here, showing that somehow they're actually inhibiting the production of carbon monoxide, which is not great. But our sort of longer chain copper complex was slightly better for carbon monoxide production, which leads into sort of the selectivity towards products. So our shorter chain carbon copper complex is more selective towards hydrogen. So maybe this is better to test in just hydrogen evolution conditions instead of having it saturated with CO2. And then our longer chain copper complex is more selective towards CO production. So that'll be more interested to do longer runs on that and see if the activity is ongoing still. But again, the hydrogen is dominant. So looking at the sort of efficiency of these catalysts, we want every electron that we put in to be turned into a product. So if that happened, everything would add up to 100%, sort of one, these red lines up here. As we can see, we're missing, in some cases, quite a lot of our current. So then we think, what about the liquid products? Formate is a value-added carbon product. is estimated to be about $1,000 to $1,700 per ton. And so we can see in these sort of areas, we're missing quite a lot of current. So we would do longer runs at these potentials and then identify how much formate we're making, if that's the product we're making in this case. We are getting formate in some cases, but we haven't done these runs quite yet. So in summary, hydrogen greatly outstrips our carbon monoxide production, and these are our two main products. And our copper complexes are much better than our nickel complexes. And in future, we'll possibly do some hydrogen testing, as well as longer runs for formate production, and see if that activity does continue to be ongoing. Thank you.
Okay, questions from the audience.
Hi. As you deposit the monolayer of the catalyst, is there any control to the geometry of where the active sites will end up, or is like a random?
At this point, it is random. So we could do sort of XPS in future. I think they're getting a machine up in the engineering lab soon. Then we can see what the arrangement is like on the surface, but at the moment it's just kind of random.
Do you have any guess if like controlling that geometry probably will improve your faradic efficiency?
Yes, it should do. I mean, because of the design of the catalyst itself, you've got those metal centers quite close together. If they're still stuck together on the surface, then that will be the ideal arrangements for the catalysis. But yeah, at the moment, we don't exactly know once we sprayed it on what it's like.
Thank you.
I was just wondering, so I think the carbon dioxide is really coming to your catalyst in the form of carbonate ions. Is that right?
Probably, but like, because it's like all bubbled through, it might be in a
Oh, so yeah, so can you just yeah, how is the carbon dioxide like physically introduced to the reactor?
So it's bubbled through this bubbler in here, and then it's pumped round through the cell. So it's saturated before we start. So there should be carbonate forming there, and I think the electrolyte itself forces it more towards carbonate formation. But yeah, it could be that there's bubbles flowing through here as well of carbon dioxide.
And it potentially dissolve CO2 as well? Or?
Yes, yeah.
Thanks.
Questions? I guess just if you're always introducing this CO2 with water substrate, does that mean you're always going to get, I guess, formation of hydrogen
yes
in the process?
Yeah, because that's a massive source of protons, which is in complete excess. So yeah, we're always going to get hydrogen formation in this case. Yeah, it's kind of hard to control that too much, but yeah.
Yeah, I mean, just to comment on that point, like the hydrogen, it's kind of a nice problem to have almost, and you can control. Yeah. I mean, you can adjust that with like industrially do it through water gas shift reaction or reverse water gas shift, one or the other, I can't remember. But
yes,
yeah, you can turn that back into CO through standard methods. Yeah,
yeah, definitely.
Just a quick one. The CO2 process is pressure dependent too, isn't it? What pressure do you run the reactor at?
So it's done at atmospheric pressure. So the CO2 is flowing into it at a rate of 20 mils per minute. It's probably under a higher pressure, but I don't know exactly what that pressure is.
Yep. Thank you.
Hi, just a quick one again. So your end products are carbon monoxide and hydrogen as a byproduct. Is that correct?
Yes, well, there are major products. Sorry, I kind of glossed over here. So we do get a little bit of methane and a little bit of ethylene as well, but they are quite small, so it's quite hard to quantify without quite a large amount of error at the moment. But yes, hydrogen, carbon dioxide are our major products.
Okay, so I think we'll move on to the next talk. Thank you very much for that. Oh, thanks. Okay, so our next and final speaker of this session is Phil Glassey, and he's going to talk to us about double mic, critical materials for renewable energy.
Thank you, Michael. Kia ora koutou, Phil Glassey Takawinga. I'm part of a environmental social science team, and Celia is part of that team as well from GNS. And I'm working in the energy space, and you have to wonder what a geological survey is doing in the energy space, but we've got geothermal and we're doing hydrogen, but we're also looking at perceptions of energy and energy use and trying to advocate for different types of energy use as a transition. So I'm going to talk a little bit today about what the public think about, or some public think about critical minerals. So I'll just talk briefly about the ages of elements and how they've been used in energy. And 300 years ago, there were about 3 elements that were used in energy, perhaps, and now we've moved through the current thing, and it's just about everything in the periodic table. Not just about everything for energy, but if you take digital technology in consideration, then it just is just about everything in the periodic table. And I mentioned digital technology because it's going to be very, very important in the way that we control our energy. So what are critical minerals? They could be critical elements. I'll use the term critical minerals because we're actually after the elements, but they come as minerals and they're dug out of the ground, and that's what people basically think they are. But it's those that are subject to the risk of supply disruption, and they're required for important purposes. And your important purposes depends on whether you're wanting them for defense, and that might be the US and China, for example, although China has a lot of economic gain to make out of these as well. It could be energy security like New Zealand, or it could be economic benefit like Australia and maybe China. So there's a range of them, and they vary. Why are they so important for our transition to net carbon zero? Because they are contained, and you probably all know this, they're contained in batteries, wind turbines, solar panels, and just about everything in the periodic tables in digital technology and in various forms. These will change. The way that we use generators now requires heavily on things like rare earth elements and superconductors to make them small. And a lot of these are come out of China. And I would say that at this point, the Western economies have divulged their interest in these to China because their societies wouldn't put up with some of the refinement of these products and the mining of these products. So just a little bit about mining policy and governance in New Zealand. New Zealand has a well-governed mining space. It's got green tape, it's got red tape, and it's compared to other countries, it's pretty well governed. But basically all we mine at the moment is gold, coal and iron ore, and these really aren't critical minerals, although iron ore could be one of those ones that you could consider it is. We have strong environmental, social and governance guidance in this country, and it's now been adopted by mining companies. So it's linked to a lot of international sustainability goals, living standard frameworks, and even down to regional and district council frameworks. It's catered for in our legislation and regional and district plans, but the minerals are really poorly understood, these critical minerals. We've got some work in GNS that we've done, which we've identified where they might be, but we don't really know how much they are and how easily they are accessible, and what is the quantity of these minerals. And while I say we've got good governance, the mining companies think that this is a barrier. Okay, our governance is a barrier, and it's too much to go into some of these things. This is part of previous work that we did, and there's really insufficient consultation, let alone partnership with iwi when we're talking about these minerals and extracting them. And we did some work in the Coromandel, and it was very anecdotal. I'm not saying this is very scientific or even socially scientific, but in the Coromandel, the environmental issues with mining are basically around water use, tailings, and the pollution that causes. But there are some social issues that the benefits of mining don't go beyond what people think it should. So what did we do? We did an online survey and a focus group, and this was following up the work that we did. And there is little work on this. We did an online survey. We only got 46 respondents, so it's hardly a big population. And I suspect it's very self-selecting, people who are interested. And we put it on Facebook. And we asked people, do you agree with the net carbon zero agenda? And most of them said yes. And we asked them if they've heard the term critical minerals, and most of them said yes. And these are the sorts of things that they came up with. And some of them, again, coal, gold, probably aren't critical elements in terms of what that definition I gave you before. And we asked them if they are aware of the availability between the critical minerals and New Zealand achieving net carbon zero. And most of them said yes. There was a little bit of a weirdness in some of the answers that we got here, but I won't go into that. Surprisingly, when asked, should the government allow mining of critical minerals in New Zealand to achieve our net carbon zero, most people said yes, and most people said it wouldn't matter if it was in my backyard, and this surprised us a little bit. And it comes back to a little bit what Maddie was saying about perceptions in New Zealand. You know, perceptions are that we're a green country and we don't want to have mining here. And I think there's a lot to be teased out about that. But given that there was a lot of provisos about the need for regulation, the respect for the treaty, don't touch high value conservation land, seabed, it's got to be done sustainability. And there's also commentary about not being reliant from supply from overseas. We asked people to put themselves on a spectrum between, say, prioritising extraction over the environment on the right-hand side and no loss on the left-hand side. And we got a range of values across that spectrum. We then did a focus group. We tried to go for a younger group. We went to Victoria University, Masters Geography students. They're again, a bit self-selecting. They probably had a little bit of knowledge about some of these things. And we asked them some questions and then provided them some additional information. And when we asked them about what comes into mind when you hear the term critical elements, and again, elements and minerals are interchangeable, there was a different set of attitudes came up. It was about exploitation. It was about mining. That these were the strong things that came through in the discussion and the words that they put down. And when we asked them the same question about where they should sit on the spectrum, the first thing they wanted to do was debate the scale. They wanted to say, complete loss on the right-hand side and no loss, and this one actually says some loss. So they wanted to debate that scale. And the most interesting thing about this exercise was that in the focus group, we could see people changing the position of where they were on the scale as they heard other people in the debate. Okay, so and that was really interesting. And they crossed out their marker and they put it somewhere else. They hadn't considered some of the things that were in the debate about critical minerals. And we put these two things together, although they're not necessarily comparable, but the focus group was a bit more left-hand side and the survey was a bit more right-hand side. So we haven't done a full analysis on this. We've done a bit of a subjective analysis, if you like, but we came up with four broad themes about mining critical minerals, not just in New Zealand, but globally to come from net zero. And like I said before, the participants changed their mind about extraction versus the environment. And so we need to have a debate. We need to continue this debate. And we need to break down perceptions. We need to break down that polarization that we might have in New Zealand about West Coast, dig everything up, Coromandel, leave it all alone. There was a lot of talk about sustainability and circular economies and discourses, and even degrowth and going for something other than a resource-based energy. So I don't know what that would be, maybe the sun. Anything had to be done with a social responsibility in addressing exploitation, particularly of Indigenous people, and be in partnership with Māori. And the survey group really, in their comments, came out and said that government had an opportunity to set standards both in New Zealand and externally for where we're getting the supply of these minerals that are going to make our energy transition. So it's a start of a piece of work. And we haven't got much funding, but we are going to continue this. We want a broader survey. It needs to be more random. We need to tease out some of these things about which organisations should be doing some of these things that we're talking about. When we're moving towards increasing our use of solar and wind and electric vehicles. So thanks.
Okay, any questions? There's quite a few hands. I think I'll start with you, even though Janet was.
Kia ora, thank you. I wondered if there was any mention of the idea of urban mining or anthropogenic mining, because we know that that can be a good source for some critical
There was a
minerals.
lot of talk about resource use,
Yeah.
and particularly from the focus group, and that I did have a slide here I took out that, the IEA have come out with some figures that, the recycling of materials that we need will only produce about between 10 and 30% of the demand that we need globally. And so that's not going to provide us with everything that we need. But yes, I was tasked to look at mining dumps, but it's a bit tricky. There's not a lot of, it's mainly gas at the moment that comes out of dumps. But I know there's a guy in Japan who's hoarding all the stuff, thinking it's going to be worth value in some and soon. Yeah.
Kia ora. I just wanted to reference to the survey and the focus group, and what was the percentage of Māori that participated in that survey, and also the focus group. We're talking about misconceptions before and how people would move on that continuum, and if that Māori, te ao Māori lens was within that focus group, and I wonder if that might have moved some of those participants in there as well.
The focus group had European, Australasian, Asian ethnicities represented, but there wasn't any Māori people there, so that's interesting in itself. But the the Pacific Island and other ethnicities were really underrepresented in the survey as well. And that's something that it was sort of like self-selecting, and we didn't really get that full random sample that we needed. Yeah.
Kia ora, thank you. Really interesting work. I've got two questions. One is, it would be really interesting for me and maybe the audience to know what kinds of critical minerals we have in New Zealand, if you know.
Yep.
But also, the way you've been presenting this is as if you were suggesting to the audience that because we need critical minerals in the cars and the wind turbines and the solar panels and so forth, that we would somehow be extracting them within this country and then using them within this country. But the reality is surely that international producers of these things would be buying them from New Zealand, or maybe even owning mining operations in New Zealand in order to provide the production of them overseas, because we don't produce those things here.
Yeah, okay. So I'll answer the second question first, which is a really good question. I don't think we should be digging them up, because we don't refine them here and we don't manufacture the products that they go into here. And so to ship them overseas, this is my own personal opinion, to ship them overseas and have them refined there with all the carbon associated and not knowing what's happening overseas and where they go in the supply chain, I personally don't think that's a good idea. However, we might have to at least understand the resource so we know what it is for reserve when somebody actually does really need it. And so this is part of the debate. Should we be doing that? And when some of these materials, they do have nasty toxic waste products, particularly the rare earth elements, the nuclides. So do we want that in New Zealand? But I think the objective of our work is to start the debate on this, okay. And so it's all very well for us to say we're nice, clean and green, but what's happening in other parts of the world where there's those social inequities, the child slave labor, the health and safety issues, the land that being stolen, all those sorts of things is happening. And do we have a right to do that? The first question is, we have a lot of minerals, have a lot of rare earth elements in this country. We have lithium. Geo40 are trying to look at extracting lithium from geothermal steam. We have a lot of nickel. I'm not sure how useful that's going to be. But the technology is changing all the time. I saw a blade battery, lithium iron phosphorus battery produced in China. It will last 30 years. You can puncture it, it won't catch a fire. It's all recyclable. And then it will do another 30 years and light somebody's lights up in their house. So the technology is changing all the time, and the minerals that we need will change all the time.
Last quick question. I was just wondering if there's any published representative surveys of attitudes to mining in New Zealand that you could use to cross-check your results against, just to see if it is likely to be a biased sample, or if it's potentially something that is worth remarking on it and showing.
We found it very difficult to find any work that's been done on this. And one part, there's a slide missing again here because I didn't have time. Stratera, who are the mining advocacy agency for the minerals industry in New Zealand, did a survey on mining, and I for the life of me, I can't find it again. I found it once. Not sure what the population of it was, but people were happy to have coal and gold extracted. It was mainly about coal and gold, and coal. And so I don't know how our survey compares with the representation. We just don't know. We need to do more work on that to find it. Yeah. Thanks, Michael.
Thank you. Thank you very much. Thanks, Phil, again for his talk. Okay, so that brings us to the close of the first day, and it's been pretty exhausting. Really informative, and lots of kind of brain work required to digest all those talks. So we do have our dinner at 6 p.m. This evening. So there's a bit of time from now until then for you to rest up. It's pretty easy to find, but a group of us will be leaving from here. I mean, it's sort of 5 minutes walk from here. So a group of us will be leaving sometime between 5 and 6 if you don't know the way. Yeah, so I'll at least be walking over there. So if you want to come with me. And we're starting at 9 a.m. sharp tomorrow morning. Thank you all for a really a great first day, and we'll see you either at the dinner or tomorrow. So thanks a lot.